Our next speaker is going to be Tim Rooney from BT Diamond. Tim is a product director or product management director for BT. BT is one of our sponsors. You'll be able to find them over here during lunch and during breaks. They also make IP address management appliances and applications and related software. Also managed services. I have to put those in. Tim is responsible for directing product and feature development, maximizing profitability, managing partnerships, supporting sales, and a whole bunch of other things that he probably adds to his resume on a regular basis with those other duties as assigned. So please welcome Tim Rooney.
Thanks, Dan. Thank you very much. So I'm actually going to talk about a topic that perhaps builds on the last presentation and even maybe the one before that by Jeff, and it's really about Internet of Things and IP address management. So I think Jeff's slide was very telling in terms of the growth of the Internet, in terms of the number of devices out there, is largely going to be fueled by these things that get deployed. Traditionally, the Internet, of course, has been comprised of our laptops, our mobile devices, our tablets, what have you. But now that the technologies have really kind of converged with respect to processing power with some of the technologies in wireless communications, it's really brought about this whole environment where there are now unstaffed or unmanned things that can be deployed in a network that can perform various functions for monitoring, for controls, actuation, video surveillance, etc. So we're going to talk about, just to kind of level set, I think everybody's heard of what the Internet of Things is and what it can offer, but we're just going to talk about some sample applications. Maybe it'll spur some imagination. I think it's a very new industry right now, and it's very ripe for innovation and development of new applications. Then we'll talk about IP addressing in an IoT environment. So again, building on a little bit of what we just talked about, and then talk about IPv6. I think the group here would agree that IPv6 is always going to be recommended. However, it may not always be necessary. There may be some edge cases where those people grasping on to the remaining fragments of IPv4 space may want to do so as well. Automating address assignments and IP address management strategies. So some of the applications, whenever you hear the word smart as a descriptor for something, a smart home, a smart TV, a smart car, a smart city, it's likely that involves some deployment of Internet of Things. So the idea of something smart, let's say when you say somebody is smart, they probably make a lot of good decisions, come off as being someone who knows what they're talking about, right? So the idea here is analogous. So you've got these sensors or these devices out there, perhaps throughout your network or throughout your enterprise, and it's actually feeding you information. They're feeding you measurements, maybe little bits of information that feed back into your processing engine, if you will, kind of your big data engine to process all these inputs, all these measurements, and enable the decision process to occur, and hopefully good decisions based on that data. So the idea is very analogous, really getting eyes and ears out into your environment and attaching those eyes and ears to your network is kind of the concept. So, so again, transportation industry has really been among the leaders in IoT. Really, they've been doing it for probably over a decade now with RFID in the early stages, but certainly they've been a leader. Healthcare, I think these days you have major surgery and you're out of the hospital the next day, if not the same day. So the idea of reducing costs really across any industry and being able to monitor your vital statistics remotely is an important aspect of some of the research going on in healthcare. And then on the enterprise side, really it's pretty wide open. It's really with respect to the business that the enterprise is in. If there's a way that you can make your processes more efficient by having more data, more information on how you do business, how your customers like your products, all of these things, if you can measure that through a sensor of some sort, then that can provide vital information for you to perhaps run your business more efficiently. So the way I like to think about IoT is more eyes and ears, more data out there that you can process and hopefully make smart decisions. And from a basic architecture perspective, just a very high-level diagram here, you kind of have your area networks here where you've got your sensors or whatever things that you deploy, and you may have things for multiple thing types for multiple types of applications. And they basically are feeding back through what I'm calling here an aggregator, which is really an M2M term. But from a IPv6 perspective or from a IoT perspective, it's maybe perhaps a border router is a better term. So it's really bordering this area network where you've got these things deployed and bordering that into your perhaps enterprise network or the internet in itself. And the reason I draw the picture this way is that this is actually going to influence perhaps your address planning and your address management techniques with respect to going through, your enterprise network. Maybe it's within a closed environment. Maybe it's your manufacturing facility that you're measuring the weight or the temperature or the pressure of certain things along your manufacturing line. And perhaps that all resides internally, and that may have an influence on what address strategy you go with. On the other hand, if you've got things kind of out in the wild, from a municipal application perspective, maybe you're measuring traffic, things out. We have actually a BT as a customer where we're actually helping them monitor their pipelines to make sure or to detect any kind of leakages. They measure the pressure on the line to detect any drop that might indicate a leak or a crack or a break altogether. And so you've got these sensors on these pipelines, and of course pipelines are, for the most part, routed in areas that are uninhabited for the most part. Not a lot of good cell coverage there. So you've got these devices out there that access the internet, perhaps by meshing together and hopping on each other, as we kind of show here as well, but accessing the internet. And that's, of course, is going to play a role also in your address planning and your address strategy, because to access the internet, of course, you need a public IP address. In many cases, you might see a case where you have both situations where you've got internet and enterprise networking, and then the application server is kind of our collector and processor of these measurements, and hopefully providing good data for good decisions. So just taking a quick look at the internet stack that we all know and love. Really starting at the bottom, we have basically the Ethernets, the Wi-Fi type of data link and physical layers. Building on that, of course, v4, v6, UDP, TCP, and then the application layer, which I'm honed in on here on HTTP, because basically the internet existed, for basically 25 years before it became a common term in everyday parlance. And now the reason for that was really because of HTTP and the World Wide Web. So the internet became the web, and therefore it really took off with respect to adoptability. So from a thing perspective, I'm happy to see that the IETF is following a similar model. And things can follow the basic internet stack as we show here, but things that are deployed on pipelines in remote areas, they're working in a more harsh environment, and they may not have the luxury of connecting to an Ethernet port or even a wide area 4G type of wireless connection. So the IEEE has defined, again, starting at the bottom of the stack here, for these so-called constrained environments where you don't have the luxury of a broadband connection. The 802.15.4 was developed by the IEEE to provide a link layer and physical layer for wireless communications for short range, 100 to 10 to 100 meters, for example, and it provides very short frame sizes. So it's really developed to exist in an environment where short bursts of communications might be more effective to communicate through. So working IPv6 on an environment like that, as you can imagine, with the MTU being 1280 bytes and a frame size of 128 bytes, it might be a little difficult to shoehorn that into a frame. So the 6LoWPAN working group, which has since been retired, but the work is taken up by other working groups within the IETF, was defined to enable the adaptation of IPv6 packets into the 802.15.4 through header compression, also fragmentation reassembly, and also layer 2 forwarding. And we're working up the stack. UDP primarily, TCP can be used as well, but just from the burstiness of things, UDP might be more appropriate. COAP is the constrained application protocol, and the model here is really an HTTP-like protocol to enable the interfacing through a REST API to the application, really following a similar model to what really led to the explosion of the internet, the web. And so the COAP interfacing, perhaps through REST, just provides more of a unified REST API at the application layer. So the end goal is to provide a common application and REST interface that can be leveraged, whether it's a constrained or an unconstrained environment, to enable that really the Internet of Things to really be the Internet. So it's all one Internet comprised of our user devices, but also these things that are out there in the being monitored by organizations. So if you are an organization, let's say you've got an IP network you're managing today, well, maybe I can make my organization smarter and deploy some things out there. How's that going to impact my network? Well, certainly scale is one area. So if you've got many of these things, the more eyes and ears you get out there, presumably the more granular the data you're going to get. So generally a good thing. But the scale is going to impact, well, now I've got all these things that are on my network that I have to take care of and keep an eye on. So that's one aspect, whether it's private or public, again, whether you're going up through the enterprise cloud or through the internet or both, your network infrastructure to support those things. So there's border routers, for example, among other infrastructure that you might require. Security. Security is obviously a big area for any IT or operations planner or engineer. And so these things, really going through the due diligence in terms of validating the hardening of those things from penetration. Obviously, if someone should compromise a thing that could be perhaps used as a stepping stone within the network. So something to think about there, but also just from a network access and accessibility perspective, having things popping up on your network, it may be something of concern to think about. Network management, of course, these things are on your network that you might want to keep an eye on them, make sure the battery's still running and it's still reachable, et cetera. And then, of course, IP address planning. So that's really where we're going to kind of launch from here and jump into more of the IP addressing aspects of IoT deployments. So just in all fairness, I have to bring up the case for possibly clinging on to IPv4. There are organizations out there. I think a lot of the discussion so far has been around the early adoption of IPv6 among enterprises for various reasons. And I think an IoT type deployment could apply with IPv4 in environments where you have a perhaps limited scope. Perhaps it's a manufacturing facility, for example. Sufficient private address space exists so that if you've got enough IPv4 space, there's no internet access required. And also static deployments where it's a fixed kind of implementation. Contrasting that with the need for IPv6, certainly from a larger scale perspective, coupled with the need for internet access, is really where you're going to need to, by necessity, go to IPv6 just for the public address scalability. Agility really comes in the form of if you've got applications where you need to quickly set up a network and basically put it together for a show, such as an event like this, or what have you, depending on the business you're in. Agility is also another benefit of IPv6 with some of the SLAAC features that we'll talk about in just a moment. And also the constrained environment support. I don't think IPv4 is precluded per se from the constrained environment, but it really is focused on IPv6 within the standards bodies. Self-initialization, just putting a device out there and having it pop on your network, that's a convenience as well. And also, as we like to say, IPv6 is the internet protocol. IPv4 is becoming the legacy protocol, at least at some point. So in terms of defining how these things on your network are going to impact your addressing plan, the first step in defining your address plan, of course, is, I need to provide an IP address to something that I want to have on my IP network, whether it's the internet or my enterprise network. So at bottom, the base requirement is to provide an IP address to these end nodes, but there's more power than just providing an IP address. You can actually use that IP address to your advantage in terms of how you configure it and allow it access, some of the policy-based discussions we've had earlier, allow it to communicate with other nodes across the region or not. You may not want somebody in finance to access your things out there, so having the ability to define policies to cordon off certain areas of your network or devices is one key consideration. and also even just internet access, whether you want to constrain that. Enable end nodes to communicate via supported media. So maybe these things have actual special routing requirements, routing treatment, like voice traffic versus data. There may be thing-specific treatment that is required that you can also use your address plan to influence that. Facilitate network management and security management, really the other two areas that we've touched on earlier, just in terms of the ability that your address plan has, the power it gives you to really help facilitate the formulation and the easing of not only the initial address assignment, but your ongoing management day to day in the months and years to come with respect to managing your network and also applying security policies. So if you're wondering how is this really the case, let's take a quick look at an example. So if we start with our basic reference network, good old 2001 DB832, and let's say we want to allocate the first nibble here on an application basis. So again, not going to the first network topology level hierarchy that we typically historically have done, but let's look at applications. So let's say I've got 4 applications that I want to allocate space for. I might have additional ones, obviously, for thing-specific applications as well. But the benefit here is that, as you can see, I've got, for my voice traffic, if I need to apply a policy or if I need to shut down the voice traffic for whatever reason, it's really one entry in my policies that I have to make. Okay, so your top-level allocation is really going to be, from a policy enforcement perspective, the simplest to enforce or to enact within your network. So the next layer, if we look at by region, let's take the next nibble down. And so I'm drilling into the voice area, which is 8,000, and voice in Philly is 8,800 in the third SEDECTET there. So this then illustrates the fact that you can again see the by site management that you have. You can look at recognizing those hex digits as my application and my location, my site, right by looking at it. But on the flip side, it does actually increase the number. In this case, if these are your core routes that you need to track, it's going to be one route per application, basically, given the way you've structured it in this manner. So there's a trade-off there with respect to the ease of policy deployment based on IP addresses, and then the corresponding impact on the number of entries you have to make. And then one more layer, if we look at by business unit, if you wanted to set up different administrative domains, here you see that further illustrated where I've got to now make, in this case, 16 policy entries per business unit, assuming there's a presence in each network and for each application. And so it's more entries or more granularity of what I need to manage from a network management and a security management perspective. So hopefully this just gives you a quick example. Obviously, you can play around with this, and the question about what do you allocate first or by topology or what have you. I mean, I agree with the comment before. It's really what works for you and what do you do most in your network today. You can leverage that history and try to make a decision based on what's going to make your life easier in the future. So just from a general perspective, defining your addressing requirements. Where do you need addresses? Obviously, again, enabling the end nodes to get addresses to communicate. Defining your hierarchy layers. So defining, whether for you it's application, then site, then business unit, or whether it's some other stratification that you want to assign, considering the various layer types and some of your Internet of Things deployments, any special requirements there. And allocating them within your structure of your address space. In terms of allocation strategies, I think, again, the common, approach or recommended approach that I haven't heard any diversions from this is really the nibble boundary, again, for readability, as we saw in the example, but also for DNS. So if you're mapping back to DNS domains, IP6.ARPA domains, having it on a nibble boundary is going to make life a heck of a lot easier if you're not delving into like RFC 2317 style breakups of nibbles. So help simplify DNS and then by site recognition. And then also, I didn't touch on the allocation mechanics, but sparse allocation at your top layers just gives you more space to just allocate, change the mask size basically, or the prefix length, instead of having to allocate additional blocks. So sparse allocation gives you that added benefit, and then maybe best fit or random at lower layers. So that's kind of the block level view. Let's kind of delve down now into the individual address assignment perspective. And, for assigning these things, IP addresses. So again, if you've got thousands or tens of thousands of these things you're planning to deploy, a manual approach is probably not going to be very workable. Having to hire maybe a group of people to manually configure IP addresses, hopefully correctly, that's only half the battle. It's not only the configuration, it's actually the ongoing management. Someday later, should you have to renumber for whatever reason, okay, well, now you've really got another issue to have to address. So manual is an option, but not a recommended option, particularly for an IoT deployment. SLAAC, of course, is another option, basically just deploying these things out there, powering them up, letting them solicit router advertisements. There are actually special requirements that have been imposed by the constrained environments as well to make the messaging a little more efficient. Being able to define the interface ID by auto-configuration and auto-configuring its IP address, and also through duplicate address detection. Another option, if you want more control from a network management perspective, is to configure DHCP v6. So DHCP, analogous in v4, works pretty much the same in v6. But basically, it's a network server provisioned. The devices would multicast to the well-known DHCP server's address and obtain an IP address. And then the other benefit here is that you also can get additional parameters that the device might need for initialization. So it may need to know a TFTP server to get a boot file, for example. There may be application-specific servers that the thing has to know about, and DHCP is a great way to define that. And then there's a hybrid approach as well. So if you wanted to use SLAAC for the IP address initialization, and the router advertisements also have an option for DNS and domains. So if that's enough for you, SLAAC's probably okay. If there's additional information, however, you might want to supplement that with DHCP v6 for the information request to get additional parameters that that device might need to fully initialize on the network. Just to illustrate how this interacts with router advertisements, how does the thing know what it should do? So using the managed address flag, the M flag, or the other configuration flag, basically if they're both set to 0, the device knows that it has to use SLAAC to auto-configure. If the other configuration is set to 1, that says, well, okay, the managed address configuration is still off or 0, so SLAAC is used for the address configuration, but DHCP v6 would be used for the additional configuration information if required by the thing. So this is that hybrid approach. And then lastly, if the managed configuration flag is managed address configuration flag is 1, in either case of the O bit, then you've got DHCP for both, for address assignment as well as parameter initialization. So for SLAAC, just taking a look at some of the basic pros and cons. Certainly it's self-initializing, ad hoc. If you need to rapidly set up networks and tear them down, if you will, provides a great way to do that in terms of convenience. There's no need to configure a DHCP v6 server, figure out what address space I need to use, and all that configuration information. The cons, well, you really can only configure so much with SLAAC in terms of the address and maybe some other information in the router advertisement. And then also the network access permissiveness. And by that I mean basically, okay, I've got a network of SLAAC things that I'm auto-configuring through SLAAC. Well, if someone were to detect that and be able to pop a thing in there that maybe they were going to be using for some other nefarious purposes, then it could be something to be concerned with. Just a quick review of DHCP v6. Obviously, it's very similar to v4 in terms of the transactions. You can actually get it down to 2 packets with the rapid commit. It also does perform relay agent forwarding in this case to forward information from a local LAN or local network to a DHCP server elsewhere in the network. Again, using multicast as opposed to broadcast. And that's really one of the main differences here. Here you just see a breakdown of the messages for the types. Obviously, all the functions are covered, just different message names. multicast broadcast from a differences perspective, and then also the relay support. DHCP-v4 really just modifies the packet from the client, puts the GI adder in there and sends it off. Whereas with IPv6, it actually encapsulates that in a relay forward message and sends that off to the DHCP-v6 server, either through relay helper addresses that you can configure in the router or through the multicast addressing. From a feature perspective, again, a lot of similarities here. Some of the key ones, key differences, the fixed address per client, what Microsoft calls reserved addresses, what the IETF calls manual DHCP. This isn't supported in DHCP-v6 unless you know the DUID in advance. The DUID is the client identifier, and it's actually it can be based on various things, based on the link layer address plus the time. It can be based on the enterprise number of the device. It's actually derived by the device itself, so you really don't know it a priori to be able to configure that in your DHCP-v6 server to say, oh, when I see this DUID, give it this address. So that's one main difference that we've seen. Haven't seen it cause any issues at this point, but it is something to consider. Subnet allocation through DHCP, prefix delegation with v6, another benefit, we'll touch on that in a second. And then the DUID versus client ID are the main differences. And then the failover support, there's some work in progress there in terms of DHCP-v6. And really just the size of a v6 subnet might make sense in the meantime to do a split scope type of environment where you've got two pools on two different servers for the same subnet. Just makes it a lot easier to deploy and manage. As I mentioned, prefix delegation. So it's really just the allocation of subnets, not just individual IP addresses. So this might come into play in an IoT environment where you've got your border routers. Let's say I need to set up a thing network here in this room here. Let's say for the 30-minute abs, I wanted to deploy weight sensors on everyone's chair and kind of measure the weight differential through that presentation. To do that, I could just basically set up my border router as well, have them communicate to the border router, and then just allocate a subnet through prefix delegation. So again, depending on the application of your things and whether you need to set them up quickly and you don't want to manually configure subnets, you can do that through prefix delegation. From a DNS perspective, I touched on this a little bit earlier with respect to the IP6.ARPA zones and nipple boundaries. A lot of this, how much you delve into DNS is really going to come down to, how you want to manage these things. Do you want to manage them or access them by name, where that's obviously going to require you to update DNS. See an example of the quad A record there. And then also for the reverse. So a lot of VPN type applications will look for the existence of a PTR record for a device that's trying to connect to the VPN gateway. So if that's a concern, or similar applications that require the existence of a PTR, that likewise would necessitate your configuring of those PTR records in DNS. In terms of summarizing the IP address management for IoT, certainly the block space strategy with respect to the various layers, any kind of thing-specific policy treatment that you might need to apply, the individual thing address assignment policies. Do you want to use SLAAC, DHCP? Is there a need for additional parameter initialization? And then if so, deployment of network services to support that, DHCP, DNS, and perhaps others that might be required to initialize your things deployed on your network. So in terms of selecting an IPAM methodology, we're kind of going to look at a couple ends of the continuum, if you will. We're going to kind of look at the tried and true trusted spreadsheet model that a lot of folks still use today for managing IPv4 address space. And then we're going to look at that compared with a commercial IPAM system, just to look at along these 5 dimensions here, the 5 S's of determining what IPAM solution would best fit your things deployment. So we have scale in terms of the number of things, scope, internal versus external, local, global, et cetera. Speed in terms of the agility factor that I talked about. Services, do you require the deployment of network services in support of the things for initialization or for general operations? And then finally, security, access control. Security is obviously a large area, but with respect to our IP address assignment, we'll talk about it with respect to your allocation strategy, but also the individual assignment and access control. So if we look at the two ends of the continuum, again, I kind of block v4 and v6 on this too, but it's not necessarily true in all cases, as we'll see. But in terms of scale, obviously, the more devices you have, and if it does require internet or global access, that's really going to probably drive you to IPv6. And with IPv6, maybe, again, depending on the scale of your network, to an IPAM system that can help you manage that holistically with respect to your current IP address space plus your additional things deployment. Whereas with a speed in terms of the agility, again, IPv6 has the benefits of the SLAAC and prefix delegation to enable you to quickly set up networks if that's a requirement. Services, this isn't so much an IPv4 versus IPv6 criteria here. This is more of a spreadsheet versus a commercial IPAM system. If, for example, if you don't need DHCP and DNS for your things deployment, then a spreadsheet's probably fine because all you're doing is managing your IP address space. You're not deploying configurations out. But if you do require these services, an IPAM system can help you to automate or streamline that process, take the information you've already entered into the IPAM system and use that to configure your downstream services. And then likewise with security, with respect to spreadsheets versus commercial IPAM, I don't know if anyone would agree it's less critical, but it's all pretty relative, and these are all kind of qualitative scales anyway. But based on your deployment and what your thoughts are in terms of the relative importance of these, it might drive you to make a decision of, do I want to stick with spreadsheets to manage my thing deployment along with my current network, or is it a no-brainer and I just want to go with IPv6 and a commercial IPAM system? But as we all know, the real world never works out to be such clear-cut cases. So you might end up with something like this, where you've got, I've got a small scale, but I need internet access. So do I have enough address space where I can get away with v4 or not? And so this might drive you to make a decision based on one criteria or a couple, as opposed to all five agreeing. So it's really just an assessment that you'd have to make in terms of your things deployment and these various criteria to determine what makes sense for your environment. So to summarize from an IP address management perspective, it really is a critical strategic management function. So as we've touched on, it influences not only getting IP addresses out to end devices that want to communicate on your IP network, but it also plays a role in streamlining and simplifying your ongoing management of your network, as well as application of policies on your network as well. So managing your addressing hierarchy, simplifying your address allocations, again, through IPAM systems that can enable you to do that through single-click type allocations. And of course, we'd be happy to show you a demo of that at booth 6 later today, if you like. Tracking your v6 deployment. Again, if these things are part of your network, it's probably something you want to track with respect to your IP address space. Then the accountability aspect as well. So with spreadsheets, you really don't have that tracking of who made a change when. Multi-user access is also a potential stumbling block there. And also auditing of addressing who used that address 2 weeks ago yesterday. You're not going to get that through a spreadsheet alone. So an IPAM system can help you there. And then lastly, the APIs and CLIs with respect to integration either with other IT systems on a cloud type deployment environment as well. So just some of the criteria to consider. We do have, of course, additional resources available out there, white papers. We do an annual survey. We'll be doing one this summer. We typically do it around the anniversary of the World IPv6 launch, so look for that in June if you'd like to complete that. We also have some IPAM and IPv6 books, more on that in a second. We do have some free tools online as well. So we have a subnet calculator, an address planner, we've got an ROI tool, if anyone's still trying to justify to management that they need to deploy IPv6. So we've got some tools to help you hopefully there. And also a basic needs assessment. There's the short URL. Sorry, it's not a little phonetically easy to remember, but we also have the QR code there as well. If you need it, you can stop by our booth. Be happy to provide it to you. And then, of course, on social media. But speaking of the book, I just wanted to introduce Mr. Mike Dooley here. Mike, you want to stand up for a second? So Mike has been one of our really one of the founding fathers of the IPAM industry in general. He's been working in this field for 20 years, 20 plus years. And so he's really been a key person in terms of evolving the industry, moving it forward, developing new features, and really helping people to better manage their IP address space from a V4 and V6 perspective. So it's really a privilege and an honor to have co-authored this book with Mike. And so I would invite you to take the opportunity, the rare opportunity that Mike is actually out of the office, they let him out once in a while, to stop by booth 6 for a signed copy. And if you'd like me to sign it, I'd be happy to as well, but definitely want to get Mike's. And that, again, is going to be at booth 6, right over here in the next room during the beer garden, which we're sponsoring as well. With that, I will turn it over for questions, please.
Thank you. I'm going to preface the question with a couple of things. One is there's a National Science Foundation Small Business Innovation request, as well as a technology transfer that states by 2020 there's going to be 50 billion devices by 2020. I think that's a great acceleration of IPv6, and you obviously can't do that with IPv4. With that, there's kind of tied to Mr. Doyle's presentation, and the abstraction part of that is IoT 6, where there's a registry for non-IP devices or constrained devices, power, compute, and communications that are going to be on lossy networks and come on and off and not reliable. But you can register those to track them and what they are. And so the issue there is that logical abstraction and that connection through an IoT 6 gateway for those non-IP devices, sensors, and actuators that you speak of. Can you speak a little bit to IoT 6 and what that might mean? It's not the IP addressing, but it's all those devices that are non-IP.
Yeah, and I think a lot of the earlier technologies, a lot of utilities, for example, developed their own proprietary technologies. And really, I think you're hitting the nail on the head in terms of the gateway that would be required, almost like a NAT type device. But it's more than that; it's actually protocol translation. So taking the protocol that's used on the proprietary network and then converting that to IP. Technically, those things are not part of the Internet of Things because they don't use IP addresses, but they can be joined, I suppose, to the Internet. And through this proxy or gateway type of implementation that would have to be, of course, protocol specific to what you're interfacing to. So I'm not sure if that answers your question, but that would be kind of the high level approach, I'm guessing. So, and your prediction there, 50 billion, or the government's prediction, yeah, it's various predictions all over the map. Really, I know some analysts say 26 billion, some say 20 billion, but it's definitely in the tens of billions is kind of the consensus out there. So definitely a ripe field for innovation and bright ideas.
So the question in regards to what's the impact on what the HomeNet group is doing in regards to sort of routing within these topologies, because that's a challenge for these devices, right? I mean, they can't really. I'm assuming most of these devices have a battery supposed to last 5 years plus. Yeah. V6 obviously offers some efficiencies through 6LoWPAN and what they're doing there. But what do you do when you start introducing routing on top of this stuff and start introducing multiple prefixes and other things? Have there been discussions and thoughts around that? What are your?
Yeah, I know that's definitely active discussion in the IETF. I mean, I think that the 802.15.4 IEEE standard really defines for that type of environment, for devices that are constrained. Limited battery life, but you've also got limited CPU, memory, wireless range. So there's a lot of sleeping going on there, and really to preserve the battery and to keep the communications to a minimum as possible. So I think that protocol definitely helps. And then I think the 6LoWPAN on top of that definitely has really, I think that group did a great job in terms of interfacing V6 and to that environment. So I think that it's really, whether it's one prefix or multiple, it's just kind of obviously with more, presumably you're talking about more traffic maybe, but it really kind of comes down to the traffic frequency that these devices have to communicate that's going to influence the battery life and how often you have to go out and replace them, I suppose. So I'm not sure if I addressed your question or not, but I think, in other words, I think the standards have were, cognizant of that type of environment they're trying to design for, and I think did a commendable job in terms of building protocols that support that.
So, how are all these things going to interoperate? And I don't mean application-wise, I mean they're all going to exist in the same places. So, as an infrastructure provider for a campus, I have to deal with all these things. Mm-hmm. And more importantly, I don't think people are looking at, they're all using the same ISM radio bands. And so what is this little battery device that wants to talk on 2.4 going to do when it can't get clear? It's going to sit there waiting for a channel forever and ever and ever, and its battery's going to die because it's sitting there waiting for a channel. Yeah. I don't think people have thought through some of these things in practical.
No pun intended, yeah. No, I think, well, it kind of comes down to capacity management of the wireless link in that case. So I think that who's ever designing, if it's a local facility you're designing for, I think it's going to depend on the density of these things that you have out there, the frequency with which they need to report updates or which you want to poll for updates, and try to engineer that really would be ideally the answer.
But the point I'm talking about, though, is that it's using the same 2.4 channels that Wi-Fi is. So if that's existing and so all of our laptops and all of our devices are all wireless, and they're all using the same frequencies, and so there's certain assumptions being made, and when you add up all the assumptions, you end up with a
oversubscribed.
Yeah.
Yeah, right. Well, yeah. And I think I would give you the same answer, but just kind of expand the scope to include the non-things in terms of that wireless budget, as they call it. So being able to design the air interface such that it has the capacity, or if it needs to be supplemented with micro pico cells, what have you, whatever type of technology you're using. But that's really what it's going to have to come down to in terms of getting that capacity out there. It really comes down to that. Any other questions? Okay.
Okay, thanks, Tim.
Thank you very much.